Dear students, in the last class we have to discuss some properties of a cyclic group and then prove some results on the cyclic group. How to, if G is a generator, then G to the power K is also generator, how we find the all these generators, and we have to, in the end we have to try to solve one or two examples in this using these theorems. So, now in this lecture we also continue to some examples and also discuss some problems in this regard. The first example in this case, we have to starting, suppose we have a let G be a group of order 7 generated by G. So, because n is equal to 7, then you know that n if n is a prime, the definition means n is equal to so k is any value for 1 to 6, all are values for this 7 is relatively prime to 1 to 6. Therefore, each of these values of a k g to the power k generates the entire group. Because of the primes, 7 is equal to prime, so GCD of a k 7 is equal to 1, and then we have a g to the power 1 is a generator, g is equal to g square can generate the whole group. Similarly, g cube and all g to the power 6. So, this means all are 1 to 6 are relatively prime to 7, and that means g to the power k generate the all the powers are g to 1, 2, to the power 3, g to the power 4, 5 and 6 are generate the entire group. So, in this case we have a prime, we have to just say that because is the order of a group is a prime, then this n should be relatively prime to all the your n minus 1 elements is there. Now, we have to prove the fundamental theorem of a finite cyclic group. He is saying that let G be a group generated by G be a cyclic group of order n, and he says that if H is a any subgroup of a G, then H can be generated by G to the power D for some D divides n. So, this is means some C D divides n. And also, if we say that if H is a any subgroup of a G and order of H is equal to K, then K should divides n. And also, if we say that if K divides n, and then a generator of a G to the power n by K is a unique subgroup of a G of order K. So, now we have to list proof this theorem by the theorem we have to proving this H is a cyclic group and order of a G is equal to n is clearly is a finite, then H can be generated by G to the power m, where m should be greater than 0. So, let D is equal to, we have to the GCD of m and n, and since D divides n, it is sufficient to show that H is equal to G to the power D. So, we just say that but D divides m also. So, m can be written as a q into D, where q is the element of a z, then G to the power m can be written as a G to the power D to the power q, and that means we can say that G to the power m is the belongs to the generator of G to the power D. And if G to the power m, and then we have to just say that hence H is equal to G to the power m, and then this G to the power m containing into the G to the power generator of a G to the power D. But D can be written as a R plus Rm plus Sn, where R and S are the Z by the division of the algorithm. So, G to the power D can be written as G to the power Rm plus Sn. So, we just say that G to the power R m into S, G to the power m to the power m n to the power S, and G to the power m to the power R and to G to the power n is equal to identity. So, we can say that is identity to the power S. So, clearly G to the power m to the power m, R, then G to the power can be written as a some powers of this element, and if is written that some power that is belong to the generator of G to the power m, and G to the power generator G to the power m is equal to H. So, we can say that G to the power D is the element of a H. So, this means G to the power D containing into the H, and we have already shown that H is containing generated by G to the power D, and then we have to say that hence generator of G to the power D is the same as H. So, this is clearly we have to take into this form. By the part 2 we have by the this first part we have to already prove that H can be written as a generator of G to the power D, and where n should D should divides n, and we can say that suppose H k is equal to order of a H. So, if k is equal to order of H and and so n uh, is equal to n divides d, so k divides n. So, similarly we just say that suppose k is any subgroup of G of order k, then k can be written as a G to the power m, where m should divides n. Then k can be written as a order of a k. This order of size of a k is equal to order of a G to the power m, and G to the power n is n divides m. So, we just say that so m is equal to n divides k. So, k can be written as a G to the power n over k, and this proves the C part of this theorem. So, now there is a corollary. We can say that the number of subgroups of a finite cyclic group G of order n equal to the number of positive divisors of n. And the second thing is saying that for each positive divisors k of n, the set generated n by k is the unique subgroup of Zn of order k. So, for example, suppose a cyclic group of order 20, then we can say that every subgroup of every subgroup, already know that every subgroup of a cyclic group is a cyclic. So, every subgroup is cyclic, and there are a unique subgroup of each of order divisor over 20, 1, 2, 4, 5, 10 and 20, and then we can say that G, if G has a generator G, then the generators of these subgroups can be chosen to be G20 over 1 is equal to G to the power 20, G20 over 2 G to the power 10, G20 over 4 G to the power 5, G25 G to the power 4, and G to the power 2 and 2 are respectively. So, we can, if G is the generator of this, then by the theorem we can previously just prove a theorem, we can say that G to the power D by n. So, this is G to the power D, D divides n. So, we have just a 20 n divides d. So, n by this is 20, and these are the unique subgroup of each which are possible are the 1, 2, 4, 5, 10 and 20. And in this case we can say that clearly these are the possible, if G is a generator, then subgroups can be chosen into this form: G to the power 20 generated by G to the power 10 and G to the power 5, G to the power 4 and G to the power 2, and G are the generators of a subgroup is there. Another example we have to take in the form, suppose we have a in Z10 generated by 1. So, the subgroup 1 is the unique subgroup of order because 10 divides 1 10, and also we have the, so the subgroup generated by 2 is a unique subgroup of a 10 over 2 is equal to 5, unique subgroup of a 5 generated 5 is equal to 2, and then we have a 10 is equal to identity. So, we have a unique subgroup of a 10 is equal to 0 is equal to 10 by 10 is equal to identity element. In Z10 we have a generated by 0, we have to just say that all these things is equal to, these are the subgroup of a generated by this thing. Now we have to one example, find the number of a subgroups of Z720. So, we have to write this Z prime factorization of a Z720 is 7 just 2 to the power 4 into 3 to the power 2 and 5 to the power 1. So, number of a divisor of a 720s are 4 plus 1, 3, 2 plus 1, 1 plus 1. So, 4 plus 1 into 2 plus 1 into 1 plus 1, and that is equal to total 30. Hence, the Z720 has a 30 subgroups are there. So, Z720 has a 30 subgroups. So, another example we take, suppose U30, then list of the cyclic subgroups of a U30. We take a U30 are the these are the element of a U30. So we have a 1, 7, 11, 13, 17, 19, 23 and 29 are the which are these are the element which are relatively prime to 30. So the element of this is equal to, so we have just say that into this, then we have to say that the size of this U30 is equal to number of element in this set. We have 8. Okay. So we have just said that n is equal to, we have a 8. So of course all cyclic subgroups of a U30 are the form of a generated by G. G is belong to the U30. So clearly 1 generated by itself only, there is no other element can be generated in this form. Now we have a, suppose we have to take in 7, so 7 square is equal to 19 or mod 30, 7 cube is equal to 13. So we have a 19 we have to getting this, 7 3 is equal to 13, 13 we have to getting this, 7 to the power 4 is equal to 1 if we have to getting this. Now 7 to the power, so we have no other, 7 to the power 5 we have to, again we have to repetition is start. So 7 to the power is equal to we can say into this form. So this is only possible generated by 7 are the 1 we have a 1, 7, 13 and 19. Now we have to take a 11. So we take a 11 square is equal to 1 mod 30 implies that generated by only this. We have a identity element is getting, then we have to again cube is also we have a this form in this. So 11 is equal to 1 and 11 are the this. Suppose 17, next element is we have a 17. 17 square is equal to 19, 17 to power 3 is equal to 23, 7 to the power 4 is equal to 1. So you have a 1, 17, 19 and 23 are generated by 17. So these are the subgroups generated by 17. Then we have a 19 and already 19 generated by 19 we have a this type. So we have to just take a another element is a 29, 23 is also here, 19 is here. So we have a 29 to the power 1 this is equal to mod 30 and we have to just say that so we have a 1 and 29 are this for generated by this. So 7 is equal to 7 cube is equal to 13, 17, 17 cube is equal to 23 and because 4 and 3 are relatively prime. So therefore we have the following distinct subgroups 1, 7, 17, 11, 19 and 29. These are the only distinct subgroup of the case of we have a in this case. So we have to this clearly we have to show that this one these are the 1, 2, 3, 4, 5, 6 distinct distinct cyclic subgroup of U30. Another example we have to, but note that U30 itself is not a cyclic group. And then we have to just say that U30 itself is not a cyclic group, but we can find there is a 6 distinct cyclic subgroup of this. So we have a subgroups clearly these are the this is a subgroup, you can easily calculating this form, this is a subgroup, we have this is also a subgroup. So all are 7, 1, 7, 17 because this is a trivial and then U30 itself is this. Clearly we have to just say that these are the subgroups and these but U30 itself is not a cyclic group, but we have find a distinct cyclic subgroup of this. Now we have to prove the one problem. The problem is saying that if G is a group and G is the element of a G and G to the power 12 is equal to identity, that means we can say that order of a G is equal to we have a 12. So what we can say the order of a G is clearly we have to positive we have to find the divisor of 12. So by the theorem order of a G should divide 12. So possible order of a G is 1, 2 factors of 1, 2, 3, 4, 6 or 12. So now we have to just say that these are the possible orders of this clearly possible order of G is possibility is equal to, because we have to find G to the power n is equal to 12 is an identity. Maybe before this is also some element where is a, because order of this element is the least positive integer when we have to getting the identity element n. So, what is the possible order 1, possible 2, 3, 4, 6 or 12, maybe this form. Now we have to prove another. Uh, so we have to take a let G be a group such that order of a G is equal to 12. Here we can say that order of a G is equal to 12. Let us find the orders of G to the power 3, G to the power 5, 6, 7, 8, 9, 10 and 11. We have to find all the elements of order of a G cube, G5, 6, 7, 9. Now, we can use one of the result. We can say that order of a G to the power k is the same as a n and GCD of k n to n. So, then order of a G to the power k is equal to this form, n divide the GCD of kn, and so we have to just say that. There is, for example, 3. Then 3 and 12 are not a relatively prime. So, that means you have a n is equal to order of a G is equal to 12, and then GCD of a is equal to, we have a 12 and 3. So, 12 and 3 is equal to 3. So, we have a 3 is equal to 4. So, order of, we have to just say n is equal to order of a G, n is equal to 12. So, this means m is equal to, we have a 12, and so m is equal to, we can say that m is equal to, we take a GCD of k into n, and k we have a 12, and k is equal to, we have to take a 3, that is equal to m is equal to 3. So, order of a G to the power m is equal to 12 in this form. So, clearly G to the power but 5 and 12 are relatively prime. So, 5 and 12 is relatively prime, then order of G to the power 5 is equal to 12, and 6 and 12, GCD of a 6 and 12 is equal to 6. So, order of a G to the power 6 is equal to 2, order of a this is equal to 4, and order of a 5 is equal to 12. 7 is also relatively prime to 5, then the order of a G to the power 7 is the same as a so we have to just say that 5, 7 and 11 are co-prime to 12. So that G to the power 5 is equal to 12, G to the power 7 is equal to 12, G to the power 11 also is equal to, we have to prove into 12. So, we have to find the order of a G to the power 3, 5, 6, 7 and G to the power 11. Now, we have a left is these 3. So, we have to find again these order of a G to the power 8 and G to the power 9 and G to the power 10. So, order of a G to the power 8, we can find this in the form order of, this can be order of G to the power 8 is equal to n is equal to 12, then we have a divide GCD over k is equal to 8 and 12, then we have to find the what is the order of a GCD of a 8 and 12. So, GCD of 8 and 12 is equal to 4, and then 8 or 12 is equal to is equal to 4, then order of a this is equal to, we have a 3. Now, we have to find the another order of 9, then 12 upon GCD of a 9 and 12, this is, I break it in missing. Then again 9 and 12 is equal to 3. So, again we have a 4th order of a G to the power 9 is equal to 4. Then again we have a this 10, 12 of GCD is equal to, you have a this form. So, GCD over 10 and 12, 10 and 12 are we have a relatively prime to sorry, GCD of 10 and 12 is equal to 2. So, this is order of a this is equal to 0. So, we have to find all the powers elements order of all the powers of the elements. So, we have to just complete it into this form. This problem is completed, we have to this form. Now, next problem is saying that let G is equal to generated by G be a cyclic group of order 10 and the find all generators of a G. We have to find all the generators of a G. So, be cyclic group of order 10 means G to the power 10 is equal to, we have a identity. So, we have to, since G is a cyclic of order 10, so G can be all the distinct elements powers of this G square up to G to the power 9. We have to just say that if generated by G is equal to G up to G n minus 1 if the order is equal to n, and where E is the identity element and G to the power 10 is equal to identity. So, in a cyclic group of order n, an element G to the power k is a generator of a G if and only if G, k and r relatively prime. So, GCD of k and n r is equal to 1. So, we need to check only k for k lies between 1 to 9, find and find to ones where the GCD of a k and k up to 10 is equal to 1. So, we have to take k is equal to 1, then GCD of 1 and 10 is equal to 1. So, G to the power 1 or G is a generator. This thing. Now, for k is equal to 2, so GCD over 2 is equal to 2 and 10 is equal to 2. So, is not equal to, clearly is not equal to 1. So, G square is not a generator for this case. Similarly, we take a k is equal to 3 and take a 3 and 10 is a relatively prime. So, G to the power 3 is a generator of a this group. Now, if we take a k is equal to 4, then we have a GCD of a 4 and 10 again 12, again 2, and then means we can say that is not equal to 1. So, G to the power 4 again is not a generator in this case. We have k to the 5, then take a GCD of a 5 and 10 is equal to 5 again, is clearly not relatively prime. So, then G to the power 5 is again is not a generator in this case. Next 6 and 10 are also not a relatively prime. So, that GCD is equal to 2. So, G to the power 6 clearly is not a generator in this case. And if we take a 7 and 10 are relatively prime. So, that means GCD of a 7 and 10 is equal to 1. So, G to the power 7 is a generator of a in this case. Now, 8 and 10 also not a relatively prime because their GCD is equal to 2. So, G to the power 8 is not a generator of this. Now, last case G to the power we have to take a 9 and GCD of a 9 10 again relatively prime. So, G to the power 9 is also, we have to just say that into a clearly this G to the power 9 is a generator in this case. Now, we have to just say that therefore, the elements G cube, we have a G and then we have a G cube and then we have a G to the power 7 and we have a G to the power 9. There is a 4 elements which are the generator of this group is there. So, we can simply say that G cube, G7 and G9 are the generator of the group of order whenever we have an order of a group is equal to 10 is there. Another example we have to taking, suppose we have a let G be a cyclic group generated by of order 15, then find the order of G to the power 5 and G to the power 3. So, we can find order of G to the power 5 can be written as a n is equal to, you have a n over GCD of k and we have a 15 n. So, k n is equal to 15 and then we have a 15 over GCD of a 5 and 15 and then whatever this is called 5 and 15 is equal to 5. So, we have a is equal to 3. So, clearly we can say that order of a G5. So, by the definition order of a G to the power is the smallest positive integer k such that G to the power 5 to the power k is equal to identity. So, G to 5k is equal to identity. We have to find the values of a k. For what value of a k this is giving the identity. So, G has a order 15, G to the power 15 is equal to already identity. So, thus k must be the multiple of a 15. So, 5k is equal to 15 unit form some integer m. So, dividing both side by 5 then we have to k is equal to, we can 3 into m, the smallest positive k is equal to, we have to just say that is equal to the positive integer k is 3, because m is equal to, we have a some integer m is equal to 1. So k is equal to 1 is the smallest positive integer, and 3 to the power k. This is another way, and then the previous one we can just write in the different way of this, finding the order of this g to the power 5 in this way, but also you can find the order of g to the power 5 into this form also. We have n over GCD of n and k, k is equal to, you have g to the power k. So, we have a order of g to the power 5 is equal to, you have a 15, and then you have a GCD of, we have a 5 comma 15, and then 15 over 5 is equal to, you have a 3. So, in this case also we have to find the order of g to the power 5 is equal to, we can say simply is equal to 3. Now, for 3, 5 and 5 divides the 5 upon GCD of 3 and 15 is 3. So, we have a order of g to the power 3. We can just simply in this form we can write it to is equal to 5. So, this again similar, we can write 15 is equal to identity, we write in a different way. So, these examples we have to provide you a different way by the, either you can directly using into the form of we have to using the method, either you have to using this I try to find the solution into different way by the using the definition. Is the definition saying that we have to find a smallest positive integer where some power of a g to the power 3 to the power some power is equal to v is giving identity. So, 3 to the power k is equal to identity, and since order of a g is equal to 15, but we know that g to the power 5 is equal to identity, then 3k must be the one of the multiple of a 15, and then this is one of the, because we by the theorem g to the power n k r is equal to same when n should divides by this. So, 3k is equal to 15 m for some integer m, and then if we have a k is equal to, you have a 5 m, and then if we have a take m is equal to the smallest positive integer k is equal to 5. So, g to the power k is equal to, clearly is a we have to say is equal to 5, or the different way we have to using by the result, we can simply say that this also satisfy the condition for this order of this is equal to 5 in this case. So, both way here we using the definition, and then also the by the using the theorem we can find that the order of g to the power some power of a g can be easily calculated into this method. So, now I have to stop today lecture up to this example. If we have to just see in the next class, we have to try to some more solve to some more problems related to the cyclic group and find the order, some order of the groups, and then after this we complete this portion of a cyclic group, and we have to move to the next is permutation group. So, I have to stop today's lecture here. We continue in the next lecture some problems on cyclic group also. So, thank you very much.